start with the result of Fermat. A prime P is the sum of two squares if and only if P is not congruent to 3 mod 4. This is a local obstruction, right? Because 3 mod 4 isn't the sum of two squares, so certainly any prime congruent to 3 mod 4 can't be a sum of two squares. Now, like with many things, Fermat stated this. I don't think he actually proved it, but the proof was given by Euler. I think there's many proofs, but one proof given by Euler. About 100 years after Fermat made the claim, using Fermat's theory of descent, which I think still is pretty sure to prove this. For 3 squares, we have a similar result. Gauss gave the first complete proof. Positive integer n is the sum of 3 squares if and only if n is not of the form, it's not 7 mod 8 or 4 to some power times that. Again, it's a local obstruction. You can't write 7 mod 8 the sum of 3 squares mod 8. And for 4 squares, we have this result of Lagrange. Any positive integer can be written as a sum of 4 squares. And for each of these, we can even count how many ways you can write a number as a sum of 2, 3, or 4 squares. So if we let R sub k of n equal number of ways to write n as a sum of k squares, we have R2 of n is equal to some divisor sum. Sum over d dividing n. Negative 1 to the d-1. So you're counting the number of divisors congruent to 1 mod 4 of n and subtracting off the number of divisors congruent to 3 mod 4. R4 of n is equal to 8 times the sum over d dividing n. 4 doesn't divide d. So two very simple closed formulas in terms of divisor sums. And one way to prove these is via modular forms. If you let the theta function is defined to be sum over all integers of e to the 2 pi I m squared z. It's 1 plus positive integers e to the 2 pi I m squared z. By Poisson summation, you can see that beta of minus 1 over 4, oh, sorry, z here is x plus iy in the complex upper half plane. So x is a real number and y is a positive real number. Beta of minus 1 over 4z is equal to something times beta of z. In any case, if you take beta to the 4th, okay, that's going to be a power series which counts the representations of n as the sum of 4 squares. That's simply 1 plus sum equals 1 to infinity of r for n e to the 2 pi I n squared z. And this invariance raised to the 4th power, and the invariance under z goes to z plus 1, shows that beta to the 4th is, we'll find these in a minute, a modular form of weight 2 for this group gamma naught 4. Gamma naught 4 is the set of all elements in SL2Z, which are the form mod 4. So gamma equals, or gamma in SL2Z. And this vector space here of modular, holomorphic modular forms of weight 2 just means that beta to the 4th of az plus b over cz plus d is equal to cz plus d squared times beta of c for a, b, c, d. And it's holomorphic on the upper half plane. The all right. In any case, these turn out to be, these spaces of holomorphic modular forms turn out to be finite dimensional vector spaces, and we can write down the basis for M2 gamma naught 4 and write basis in terms of Eisenstein series. So if you want to construct a function which has this invariance under this group, well, you can just average over the group in terms of this, what do you call it? E2 of z is equal to sum over all c and d and z, except for 0, 0 of 1 over cz plus d. This doesn't actually converge. I mean, it converges conditionally, and this function itself is not in this space, but you can write a basis for this space in terms of this function, and this function has a simple Fourier expansion where this divisor sum you see over there. Well, actually, it's the divisor sum. Sum over keep dividing and maybe I need to multiply by pi squared or something. Okay. Summarize. We have a formula for the representation of n as a sum of 4 squares in terms of divisor sums. And we can prove that formula by expressing both the left-hand side and the right-hand side as Fourier coefficients of some nice function living in some finite dimensional vector space. I skipped R3 of n, which is more interesting. Let's go back to that. How many ways can you write a positive integer as a sum of 3 squares? R3 of n is equal to let me say that n is square free to be a little bit, make the formula a little simpler. R3 of n is equal to 24 or 12 times 12h of negative n, or 24h of negative 4n. Let me get that backwards. 12h of negative 4n. of negative n. In first case, if n is commutative to 1 to 2 mod 4. In second case, if n is commutative to 3 mod 4. Where h of negative n equals the number of SL2Z equivalence classes of binary quadratic forms, integral binary quadratic forms of discriminant negative n. Okay. So we're talking about binary quadratic forms, forms of the form ax squared plus bxy plus cy squared, where b squared minus 4ac is equal to minus n or minus 4n. And obviously SL2Z acts on these just by change of variable, changing x and y. Now we can count the number of inequivalent binary quadratic forms of discriminant. And again, you can prove this using the theory of modular forms. It's a little bit harder because theta cubed will be a modular form of weight 3 halves. It's not integral weight, so it's a little bit harder to work with. But that's not a nice proof, right? Because here you have this result that the size of some set equals the size of some other set. Okay? So you want an explanation of why these two sets have the same size. It's not just numerical equivalence, but is there some deeper reason for that? The answer is yes, and this goes back to Gauss still. So we give two explanations for this fact. Two related explanations for why sums of 3 squares should be related to class numbers of binary quadratic forms. So let's let Q be this ternary quadratic form. Now, if I have V ABC and Z3, D squared plus B squared plus C squared equals N. So it's a vector of squared n. There's my z. And look at this orthogonal complement. This is a two-dimensional sublattice of Z3. Then this ternary quadratic form restricted to the orthogonal complement of V. So this ternary quadratic form was restricted to a two-dimensional subspace is a binary quadratic form. Of discriminant negative n and negative 4, depending on which case we're in. What I mean by that is if you choose a basis for V perp, then in that basis you can write Q as a binary quadratic form. If you change the basis, then you change by SL2Z, you change the binary quadratic form by that same element of SL2Z. So you have a well-defined SL2Z equivalence class of binary quadratic forms by restricting Q to V perp. So you get a map from, we call it R3 of n. So that's the set of triples of integers a, b, c such that a squared plus b squared plus c squared is equal to n map to let me write just so I don't have to write negative n or negative 4 and pick okay the ideal class group where k is 2 is 1 square root of negative n. So the ideal class group of the ring of integers of this quadratic extension of Q, that's the same as the group of binary quadratic forms modulo the SL2Z equivalence. And sometimes more convenient to talk in this language.
So is K equal to that quadratic extension no matter the modulus mod 4?
Yeah, that's right. And again, let me assume K is square, n is square free for this. Yeah. Okay. And this isn't a bijection, this map isn't a bijection. Map isn't quite a bijection. But it almost is. Meaning there's some local obstruction again coming from genus theory, and if you ignore that local obstruction and you mod out by, maybe if I mod out by SO3Z here, mod out by some finite group, then this is a surjection onto a certain genus class, a surjection onto a certain subgroup of easily determinable index. Okay. A second explanation, also implicitly in Gauss related, for definiteness, let me say n is equivalent to 3 mod 4 and square 3. Then this set of representations of n the sum of 3 squares mod this finite group of order 48 or 24. This has an action of pick OK. And in fact, this is a principal homogeneous space. Okay. Meaning, pick OK acts on this set, and it acts transitively and without fixed points. And, a nice explanation of this is given in the paper of Alan Bird, Michelle Venkatesh. I looked on the website for my talk and I found that Joe Numbers gave me a talk tomorrow. I said, oh, maybe he's here early. So, he said, oh, no, I'm beaming in tomorrow. So it's very progressive of you guys. So let's try to explain this. Well, before I explain it, let me just point out what this means. In other words, if you have one representation, a squared plus b squared plus c squared is equal to n. If you have one representation of n as a sum of three squares, then you can get a lot more. In fact, you can get all of them. By letting the class do that. Maybe I'll just quickly get a sketch of what this action is. It's kind of nice. So starting with A, B, C, let's associate this quaternion AI plus BJ plus CK in H. Well, H denotes the space of Hurwitz quaternions. Is equal to a set of all alpha plus beta I plus gamma j plus delta k, such that alpha, beta, gamma, delta are all integers or half integers. This turns out to be a maximal order in the ring of quaternions. And this is a traceless Hurwitz quaternion.
That means it's an algebra and maximal.
It means it's an algebra and it's a, that's a ring.
So when you say half integers, you're excluding the integers themselves here.
That's right.
Yeah. That's not.
Yeah. So yeah, either all half the integers or all half times a non-integer. That's right. Okay, so let's call this x, I guess. And given, I'll call this b, given I,
The all in B or all in B plus a half.
I'm sorry,
That's what you said.
all four of them are integers or all four of them are integer plus a half. And so I need to define an action of pick OK on this set, so this pair should produce another triple, which sums of squares sums to n. Okay, so let's define this map. Define Ix mapping from K, the field. So K is still Q adjoint square root of minus n, to H. Where I just send x, I'm sorry, I just send square root of negative n to x. So we'll define a ring homomorphism. And the image of I under this map is a left ideal. I should have said, this ring is Euclidean. It's non-commutative, but it's, you know, all left ideals are left principal. So this is equal to hc times q for some quaternion q. And then finally, then let's define y to be qx, q inverse. Okay, and it's easy to check that, it's easy to check that y bar is equal to n, and y is traceless element of h again. Okay. So in other words, if y is a prime I plus b prime j plus c prime k, then a prime squared plus b prime squared plus c prime squared will again give you n. And a prime, b prime, and c prime are all integers. Okay, so this actually defines this action of pick OK on sums of three squares. Sum. All right. Let's turn to a higher dimensional analog now. So in joint work, with Valdir, we find analogous results for two-dimensional sublattices in Z4. And what do I mean? So let R for 2 of n equal the set of two-dimensional sublattices sub Z4 of discriminant n. What I mean by discriminant here is for L the discriminant of L is well, there's different ways to say it. You can say it's the discriminant of Q4 restricted to L, where Q4 is the quaternary quadratic form x squared plus y squared plus c squared plus w squared. You restrict that to this two-dimensional space, you get a binary quadratic form, and the discriminant of that binary quadratic form is what I'm calling the discriminant of this sublattice. Or it's the covolume of L tensor Q modulo L squared. I mean, very explicitly, if L is equal to the span, the z-span, the z-linear span of two vectors, v and w, then the discriminant of L is equal to Q6, let's say, of v wedge w. For two vectors in Z4, v wedge w will be a vector in 6 dimensions, or just take the sum of the squares of those coordinates. Okay, so let me write down analogs of, I think, all or many of these results. We wrote down for sums of 2, 3, or 4 squares. 1. So this is actually a result of Eka, Eileen Ziegler, and Gieser. Yeah, so Valdir, my co-author, he's a student in Input. He came to visit me for 6 months, March through end of August. And started working on this, and we're like halfway through, we discovered that these people proved like half of what we could prove roughly. But yeah, that's okay. We still have another half that we can work on. But their paper is very nice too, and their main interest is in equidistribution questions for the way these two-dimensional lattices sit in the space of, in the real Grassmann planes in R4 and related results. Okay, first, motivation. Right. This space is non-empty if and only if n is not 0, 7, 12, or 15, mod 16. So this is an analog of Lagrange's 3 squares theorem, which tells us when numbers are sum of 3 squares. 2. Okay, and what I'm writing down now, you can count the order of this set. Analogous to Gauss's theorem that R3 of n is a class number. And they could have proven this too, but it's not in the paper. Let n equal n0 f squared 4 to the beta, where n0 is square free, f is odd, and beta is 0. Okay. Then the number of planes of discriminant n is equal to some constant times R3 of n0 squared. So a class number squared, this is quantity f squared, and then times some divisor sum.
What's the range of beta?
What is the range of beta? This beta?
Yes.
It can be anything. I mean, I don't, the point is that
Wait,
the 4 part.
Anything what? An integer?
An integer, yeah. So n is an integer, so I'm taking out the 2 part or I'm taking out the 4 part, and I guess we can leave it 2 in the n0. So there's a unique way to write an integer n in this form. And I'm just writing in this form because those are the things that occur in the formula.
Yeah, I'm just worried if n beta is 2, it's divisible by 16.
Here.
So it's equal to 0 mod 16. And so this is empty.
Okay.
And you're writing a formula for it.
Yeah. That's a good point. To be safe, let me assume n is odd.
What?
Let me assume n is odd.
But then we don't need that 4 to the beta there.
Then we don't need that
That's
4 to
an
the
integer.
beta. That's right.
Okay.
Okay. And this,
Because of Rocken's theorem, Paul's has been worried about 16 since
I said,
for 50 years. So.
and I'm just writing this down to show that we can be explicit. Cn is 1, 2, 3 mod 4, and 1/3. That's 2 mod 4. 1 or 2 mod 4. But I guess I'm assuming n is odd for us. So. Omega of C is the number of prime divisors of C, and okay, this is not. This is a. Anyway, the most important case I'm interested in is when n is actually square free itself, and then you just have this number, a class number squared. Okay. 3. If n is square free, then the set of planes mod some finite group is a principal homogeneous space for kit rho k squared. K is again the internal square root of minus n. So again, all right, so what did I say? I want to give analogs of the earlier statements I've written down. Here's a description of when the set is non-empty. Here's a description of the order of this set. Here's a description of the set as a principal homogeneous space for a class group. And finally, let me give an interpretation in terms of modular forms. Actually, this is going to be a higher dimensional automorphic form of half-integral weight.
And this is the class number of k that appears.
Class number of k squared.
Yeah.
This number shows up in the Fourier extension. Fourier extension of an Eisenstein series, just like the Eisenstein series I wrote down earlier, except this is an Eisenstein series on metaplectic double cover. Double cover, which you know before. And the reason I want to write that down is, from my point of view, this explains this formula, because there's a general framework of conjectures. Say this. Okay, I'll say it like that. certain period integrals of automorphic forms, such as an Eisenstein series, a function which is invariant under, a function on GL4R which is invariant under GL4Z, GL4R, our Fourier coefficients, double cover Eisenstein series. I'm sorry. I don't think I want to say more about this right now. Just in the interest of time. And I would at least mention it because it's going to motivate one of the final things I'll say quickly. I think I'm on 3 or 2 further directions. I can see how far it is. Expect similar structure for triples of planes in Z6. Similar structure means a connection to class groups and the ability to count these things explicitly. Maybe I would say some things that are a little more interesting rather than dwell on that. Secondly, all right, so what I described earlier is for sums of 3 squares, a very explicit action of pick OK on the sum of 3 squares. Here we can show it, but it's a little less explicit. And here's a natural question. Can you write down an explicit action of pick OK squared, pick OK cross pick OK. So pick OK cross pick OK, that's actually the class group of integral cubes modulo the action of SL2Z, 3 copies of it. Okay, can you write down an explicit action of the set of integral cubes modulo the action of SL2Z cross SL2Z cross SL2Z of discriminant D, it's actually the hyperdiscriminant in this case, Cayley's hyperdiscriminant, on R4 to D. It should be possible because Bhargava showed in the first of his 3 papers on higher composition laws that this group, the set of equivalence classes of cubes modulo 3 copies of SL2Z of hyperdiscriminant D is this group. It goes here.
Triples of planes with some property. What's the property?
Triples of planes here. So triples of planes will have discriminants D, D1, D2, and D3.
What does it mean a triple of planes? 3 planes?
3 orthogonal planes.
Oh, orthogonal.
Yeah, so they'll have discriminants D1, D2, D3, and D1 times D2 times D3 will be a square. And I expect these things to have a Torsor structure for the group. Pick Q adjoin square root of D1 comma square root of D2. That's because I know what this double cover Eisenstein series on GL6 looks like. And then finally, this is one of these problems I keep returning to. Tell all my grad students to think about. But No one's making any progress. So I've talked about sums of 2 squares, sums of 3 squares, sums of 4 squares. Let's talk about sums of 5 squares. Okay. R5 of n, number of ways to write n is a sum of 5 squares. That's equal to some rational number times the zeta function at -1 at f is equal to q adjoint square root minus. So sorry, a real quadratic square root. This goes back to Hardy. Circle method. On the other hand, the order of K2OF, the known K group, is equal to, so again, some constant, there it down. And this is, I think this is just 1 or 2 for totally real quadratic fields. So that means that the number of ways to write n as a sum of 5 squares is up to some constant, the order of this group. And that's a numerical identity. Just as the previous numerical identity we had, we can ask, question, is there a natural map from this ways to write n as a sum of 5 squares to this finite abelian group, or a torsor structure, the structure of a principal homogeneous space of K2 on R5 of n, torsor structure, underlying this numerical identity. Yeah. On the one hand, unlike the higher K groups, K2 it's not that bad, right? It's pretty explicit, these symbols modulo tame symbols, and you can get a handle on computing with it, but still, I just don't know where to begin to connect it to sums of 5 squares. Okay, I'll stop here. Thank you for your attention. Questions for Gautam? Yeah.
So you were saying when you were looking at the collection of expressions of n as a sum of 3 squares,
yeah,
you could realize the quotient of that by S of 3z is a principal homogeneous space for particular k.
Yes.
And in that case, your proof sort of used this action, or this embedding of k into the integral or the
Right.
integral.
Right.
But it looks like your question B there is asking, can you do the same for this R4 too? Is it?
That's right.
So you must have proved it 3 a different way in this case.
We proved 3 a different way, yeah.
How did that-
So, yeah. So this is outlined in the very general settings outlined in Ellenberg, Michel Venkatesh, and Ellenberg and Venkatesh, is you realize these sets as orbits of the action of a delic orthogonal group on some point. And then when you do that, when you realize it as an orbit, you can show that it has a group structure, or that there's an underlying torsor structure, when the stabilizer of a point is abelian. Because then you can take double cosets at will. And in the case of Gauss sums of 3 squares, the stabilizer is just the stabilizer of a line in SO3. So that's abelian. It's SO2. And here, the stabilizer of a pair of planes. So when you have a plane of discriminant n, you take its orthogonal complement, that's also a plane of discriminant n. So the stabilizer of a pair of orthogonal planes in SO4 is just SO2 cross SO2. And that's also what happens here. The stabilizer of a triple of orthogonal planes is these 66. It's a copy of 3 SO2s.
Well, is there some geometric object behind some of these connections, like an isocene series is sort of related to a cusp in the classical case, and the ideal class group is also related to the number of cusps sometimes in certain of these hyperbolic four manifolds.
Yeah.
I'm just wondering if there's some natural hyperbolic four manifolds here. Cusps or something like that.
I see. Well, that's, again, if you write the Picard group as an angelic quotient, then yes, that's the cusps there are the order of the class group. But the Eisenstein series I'm talking about are defined over Q, actually.
What?
They're defined over the rational numbers, in my case. So, and in order to see cusps, you need to work over number fields. So, I don't see that here.
So you're working over Q.
Yeah, there's actually completely analogous questions for binary Hermitian forms. Say if you work over an imaginary quadratic number field, and maybe there, your question might be more interesting. I can talk about it.